Okay, imagine this. You try to hit a target, like way smaller than a school bus, and it's over 6 million miles away.
Right. Tiny target, huge distance.
Exactly. And then you find out the splash from hitting it actually packed like 3 times more punch than the hit itself.
Yeah, it's pretty wild stuff.
That's exactly what NASA just found out about the DART mission. So today we're doing a deep dive into that humanity's first real shot at deflecting an asteroid.
A huge success story.
Definitely a success, but also this really surprising new discovery about this powerful kick from boulders that got thrown off.
It definitely has a twist.
So yeah, our mission today is to unpack the achievement, these fascinating new findings, and what it all really means for protecting Earth from, cosmic stuff.
Sounds good. Where should we start?
Let's set the scene first. So back in September 2022, DART made headlines, right? It
Ah.
showed we could actually do something we'd never done before.
Absolutely. A real first.
For anyone who maybe missed the details, can you give us a quick recap? What was DART trying to do, and what did it, initially achieve?
Sure. So DART, that's the double asteroid redirection test. It was pretty groundbreaking. We slammed a spacecraft into Dimorphos.
That's the smaller asteroid moon.
Well, exactly, yeah. Dimorphos is about, 550-ish feet wide?
Yeah.
And it orbits a bigger asteroid, Didymos.
Okay.
The whole point was just to prove we could move an asteroid if we needed to. A kinetic impactor test.
And did it work?
Oh, absolutely.
Yeah.
Big success. DART actually shortened Dimorphos' orbit around Didymos by about 32 minutes.
Wow, 32 minutes. That's significant.
It is. It marked the
Yeah.
first time humanity deliberately, changed the motion of something out there in space, a celestial object.
And just to be clear, this Dimorphos, it was never actually a threat to us.
No, not at all. Never a threat before, not a threat after.
Yeah.
It was purely a target for the test. A safe place to try this out.
Right. Okay. So that's the part we all sort of heard about. Huge success, first time doing this. But now, like you said, there's this twist. New research, just out July 2025. What exactly did scientists figure out happened after the impact?
Well, this is where it gets really, really interesting. The impact, it didn't just change the orbit based on the direct hit alone.
Okay.
It actually blasted off this huge spray of boulders from Dimorphos' surface. A whole cloud of them.
Right. Ejecta, but boulders.
Yeah, substantial boulders. And here's the kicker. These ejected boulders somehow carried more than 3 times the momentum of the DART spacecraft itself.
Wait, 3 times? How is that even possible?
It's a lot to unpack. But this additional kick, as they're calling it, was almost as powerful in changing the orbit as the direct hit from the spacecraft.
Wow.
So it fundamentally changes the physics we need to think about for, future missions like this.
Okay.
Adds this whole unpredictable element.
That extra kick is, astounding. But how did they even see these rocks flying off, and what did their movement tell us?
Okay, so a key player was this small Italian CubeSat called Lycei Cube.
Ha! Yeah, I remember that. It flew past afterward.
Exactly. Just minutes after impact. Got these incredible close-up pictures of the whole debris cloud. You could actually see the structure.
Amazing. Any other eyes on it?
Yep. The Hubble Space Telescope also confirmed the boulders were there, helped track them over time.
So what did they find tracking them? How many? How big?
Well, astronomers managed to track 104 distinct boulders. They ranged in size from maybe under a foot across to nearly 12 feet in radius, so some pretty hefty chunks.
And fast.
Oh, yeah. Moving up to about 116 miles per hour away from Dimorphos.
Whoa.
But here's the really weird part. Tony Farnham, the lead author on this new study, pointed out that the boulders weren't scattered randomly. Instead, they were clustered in 2 pretty distinct groups.
Clustered, not just an even spray.
Nope. 2 main groups with empty space elsewhere. The biggest cluster, maybe 70% of the boulders, shot off towards the south, moving fast and at shallow angles relative to the surface.
Okay. That is specific. So if they weren't random, what's the theory? Where did these clusters actually come from?
The evidence is pointing towards something pretty cool, actually. It looks like DART's solar panels, the big wing-like things, might have hit 2 large boulders already sitting on Dimorphos' surface.
Clip them before the main impact.
Just moments before the main spacecraft body hit. They've even provisionally named these suspected source boulders, Atabac and Bodrin.
Okay.
And the theory is that that big southern cluster of ejected stuff, that's probably fragments blown off Atabac, which was a decent-sized boulder itself, maybe 10 or 11 feet across.
So it wasn't just hitting a smooth surface, it was hitting and shattering existing features first.
Exactly. It seems the spacecraft itself started this chain reaction by hitting these big rocks just before the main collision. Made it messier, I guess.
That's a really crucial detail. So this brings up a big question, doesn't it? If these boulders gave such a big extra kick and it was kind of sideways,
Perpendicular.
yeah, primarily perpendicular to DART's flight path, that's key. What does that mean if we ever have to do this for real? Deflect an asteroid actually heading for Earth.
Yeah, this is critical. That sideways momentum, that perpendicular kick. Think of it like hitting a pool ball, but not dead center.
Right, you hit it off center, it spins off unpredictably.
Exactly. Instead of just pushing it straight, you send it spinning, tumbling. This sideways kick could have tilted Dimorphos's whole orbital plane by up to 1 degree.
1 degree sounds tiny.
It does, but in space, over those distances, it's a significant change. And maybe even more importantly, it could have sent Dimorphos itself tumbling erratically.
So not just moving it, but making it unstable.
Potentially, yeah. And if you're trying to very precisely nudge an asteroid just enough to miss Earth, having it tumble uncontrollably, that introduces this huge unknown variable, makes the outcome way less certain. Precision is everything in that scenario.
So the composition and the surface really matter. It makes you think about other missions, doesn't it? How does this compare to, say, the Deep Impact mission years ago?
Oh, that's a great comparison. Really insightful.
Yeah.
So Deep Impact, that was NASA hitting Comet 9P Temple about 20 years back now.
Right, hitting a comet.
Yeah. And Temple's surface, where Deep Impact hit, it was relatively smooth, made of, like, fine uniform dust and small particles.
Okay, so a different kind of target.
Totally different. And the result, the ejected, the stuff blown off, was smooth, continuous, like a predictable spray.
But DART hit Dimorphos, which was...
Rocky, lumpy, covered in these big boulders we just talked about. So instead of a smooth spray, DART caused this chaotic filamentary ejecta.
Filamentary, like threads.
Yeah, like the material shot out in these distinct streams or threads. Not an even cloud. It was much messier, much less predictable.
So putting those side by side really shows...
It shows just how much the target's surface, its rocks, its overall makeup, fundamentally changes what happens when you hit it. And knowing that is absolutely crucial if you want your planetary defense shot to actually work as planned.
It really does sound like we're playing this high-stakes game of cosmic billiards, or cosmic pool, maybe.
That's a perfect analogy, actually.
How does that hold up, and why are these details, these subtleties, suddenly so incredibly important for the future?
Well, Jessica Sunshine, she worked on both DART and Deep Impact. She put it really well. She said something like, if an asteroid was tumbling toward us, and we knew we had to move it a specific amount, then all these subtleties become very, very important.
Right.
You can think of it as a cosmic pool game. We might miss the pocket if we don't consider all the variables.
It's the pocket, meaning the asteroid still hits Earth or hits something else, or we just don't move it correctly.
Exactly. Understanding these variables, is it rocky? Is it dusty? Will it throw off boulders? Will it tumble? How much sideways kick will we get? That's absolutely vital. We have to be sure we get the precise nudge we need every single time the stakes are real.
So, okay, we learned a lot, unexpectedly. How do we get more data? How do we make sure we don't miss that cosmic pocket next time? What's next for looking at Dimorphos?
The crucial next step is the European Space Agency's Hera mission.
Hera? Okay, what's that going to do?
Hera is scheduled to arrive at the Didymos Dimorphos system in 2026. So fairly soon. It's going to fly in and get another direct, really close-up look at the aftermath of the DART impact.
Building on DART's data.
Exactly. See the crater, measure Dimorphos's mass precisely, map its composition, get the ground truth. And interestingly, Hera will actually have to watch out for the very boulders and debris that DART created.
So DART's success created a potential hazard for the follow-up mission.
Potentially, yeah. A small hazard, but something they need to navigate. It just shows how much stuff got kicked up.
And ELISA Cube's quick flyby really showed the value of being there right away, didn't it?
Absolutely. Those close-up images it got right after impact, that gave us data we just couldn't get from Earth telescopes. Showed the structure, the filaments, proves you really need these multiple viewpoints, ideally up close, to get the full picture.
So DART wasn't just a proof of concept, it was also a huge learning experience.
A profound lesson, really. It's telling us that predicting how an asteroid reacts isn't just about how hard you hit it, the kinetic energy. It's also deeply about the material science of the asteroid itself, what it's made of, how it holds together.
Which means future plans need to account for that much more.
Definitely. Future deflection strategies probably need to prioritize characterizing the asteroid material before impact, maybe aim for different impact angles or use different amounts of energy depending on whether it's a solid rock or a rubble pile.
Yeah.
It's not just about brute force. It's about a precise, calculated nudge.
Right. So thinking ahead, imagine that future where we do need to redirect an asteroid for real. We've learned today that understanding the stuff these cosmic billiard balls are made of is just as crucial as lining up the shot itself.
Absolutely critical.
So the question for you listening is, how do you think our understanding of these cosmic pool game variables will evolve? And what other curveballs, maybe related to asteroid types we haven't even seen up close yet, might the universe still have waiting for us?
Good question to ponder.
Keep exploring the cosmos with us. Subscribe for weekly space insights.